Okay, so for this recording, we're going to go over the sample final. Now, before we start, I want to mention that after I went through them all, I realized there's a handful of questions in here that we will not be able to do because we didn't really cover them. And so either that or the problem itself has something strange about it that I will not appear on the final exam. So in other words, I'm trying only to have questions that might reasonably end up on the final exam, which I'll be posting maybe tomorrow. And so the first one, right off the bat, number 112, we're going to pull the plug on that one because it's a trick question, basically. But anyway, number 114, what's going on with that? So we look at the book. Where is it? Right here, number 114. So what they're asking us to do is find the critical points in the domains of the following functions. So we're looking now at y equals, let me write this in here, y equals x to the 3/2 power minus 3x to the 5/2 power. Okay, now the first thing we're going to do is go to Symbolab and take a look at this graph. It turns out the domain is a little unusual. All right, hold on. I had it open a second ago. Let me go get Symbolab. It's always helpful, I think, to take a look at these, at least look at a graph, before you do anything, just to get a feel for what the problem is actually asking us for. So y equals x to the 3/2 power minus 3x to the 5/2 power. All right, so if we look at the graph, yeah, it's kind of weird. It starts at 0 and then it goes up for a while and then it spikes down. So it appears that the domain is simply all reals from 0 up to infinity. And Symbolab always tells us that anyway. You can see right here. So in other words, any points we find that are negative will not count. We're only interested in critical points within the domain. Now, if you look at the graph again, you'll see that there's really only one critical point. The critical point can happen where the first derivative is 0. Let's see. Or sometimes when, let's see, hold on. When the function, the slope is undefined at that point. Okay, those would be the 2 points. Okay, so let's try this now. So the first thing we're going to do is take a function, and first things first, we have to define the first derivative. In order to find any critical value, we must know what the first derivative is. Okay, so we can easily use the power rule here on both of these terms. So remember, that means that if f of x equals x to the n power, or actually kx to the n power, then f prime of x is nkx to the n minus 1 power. Okay, so we've seen that many times. So for the first one, we'll have 3/2 x. Now when you subtract 1 from 3/2, you get 1/2. And then here, we're going to multiply the exponent of 5/2 times the coefficient of -3. So we're going to have minus 15/2. And when you subtract 1 from the exponent of 5/2, you'll end up with 3/2. So, oh, geez. Okay, so I wrote this, sorry, hold on. I wrote y. It's supposed to be f prime of x. There we go. Okay, so in other words, if f of x equals x to the 3 halves minus 3x to the 5 halves. But based on the power rule, this would be your first derivative. Now, here's what we're trying to do. We're trying to figure out where, what values of x would cause this to be equal to 0. So in other words, we're setting this whole expression equal to 0, which is equivalent to saying 3 halves x to the 1 half equals 15 halves x to the 3 halves. So what we can do is multiply both sides by 2 to get rid of those halves. So we'll have 3x to the 1 half equals 15x to the 3 halves. And of course, now we're going to divide both sides by 15. So we're going to have 1/5 x to the 1 half is x to the 3 halves. Now, I do want to point out here that x equals 0 will absolutely solve this equation. So at the very least, one of our critical points is x equals 0. But there may be another one. In fact, if you look at this graph, you'll see that one more time, it should be clear that there is a second one. You can see the peak here, the critical point, whatever that is where the tangent line will be flat or have a slope of 0. The 0 is over here. Now, because this is the starting point, the tangent line is technically undefined here, so it does qualify as a critical point. It's the second one that we want to find right now. So we're going to figure out where the slope is equal to 0. So there will be 2 critical points. And so let's divide both sides now. Okay. And of course, remember how this works. X to the m over x to the n equals x to the m minus n. So therefore here, the right-hand side, we have 3 halves minus 1 half. So this is the same thing as saying that 1/5 is x to the 2 halves. Or you can streamline this a little by noting that 1/5 equals x to the first power. And of course, this just means that x equals 1/5 is our second critical point. So there's 2 of them. And now if you look at this graph carefully, sometimes Symbolab does this. They sometimes choose very strange units here, but you see that all the way over here is 0.5. So each one of these is this is 0.1, 0.2, 0.3, 0.4, and 0.5. So right about here is 0.2 or 1/5. So we do in fact have 2 critical points. And there they are. Now you can figure out what the corresponding values of y are. We don't really need them. All right, what's next? So that was number 114. Now, number 134 on the same page. By the way, I have to do one thing here. It annoys me to no end that Word, by default, does not give you page numbers. You have to put them in yourself. And with such a long document, you're going to need them. So if you can explain to me why they would leave them out, I'd like to hear that explanation. All right. All right. So there it is. All right, good. So going forward, we'll have page numbers. Now, 134 is right here. So we're going to find local and absolute minima or maxima. So here's 134. And so the function is y equals x squared minus 1 over x minus 1. Now, we can throw this into Symbolab. You'll notice something interesting when we do that. All right, so the ratio of x squared minus 1 over x minus 1. Let's see what that looks like. So basically, it's a straight line, except that it's undefined when x equals 1. Why is that? All right, let's find out. Because you can simplify this. If you notice, the numerator is the same as x plus 1 times x minus 1. The denominator is x minus 1. So when you simplify, you're left with y equals x plus 1, which is just a straight line. So even though the function is undefined when x equals 1, if you notice it very carefully, it is a straight line with one hole in it, so to speak. There's one point of discontinuity. But if you notice, there's no point where we reach either an absolute maximum or a relative minimum or maximum for that matter. So in other words, wherever the plus and minus infinity, we would say that there are no extrema in this case. Okay. And again, once you simplify, it should be pretty clear, but having the graph in front of us is also very helpful, I would say. So that's that. Okay. Let's see what's next. Okay, so we move on to the next set. Page 406. Now, no, this is not. There's a couple that, like I said, there's a couple that we're not going to do. There's something about it that's either we never covered it or there's something very strange about it that I don't think makes sense. All right, here we go. Now, of course, 406 doesn't mean 406. There's a difference in the pagination for the PDF document as well as the, if you notice, the book says 398 when the PDF says 406. So there's a little bit of guesswork here. Here we go. So we're looking for number 228. What are we trying to, oh, there's a lot of work on this one. Oh my God. Okay, so this one is going to take a while. We have to do quite a few different things. So before we do anything else, as always, let us graph this. Okay, so we're looking at y equals x plus x squared minus x cubed. And we're basically looking for several details. We need intervals where f is increasing or decreasing, local minima or maxima, and maxima, intervals where it's concave up and down, and finally the inflection points. So we're basically going to need the first and second derivatives, and we're essentially trying to explain the behavior of this function. Okay, so let me go back to Symbolab. All right, and that way we'll get a sense of where we're going with this. Y equals x plus x squared minus x cubed. All right, let's see what this thing looks like. Now, you're going to see, because it's a cubic function, there's probably going to be two extrema, local extrema, that is. And let's confirm that. And there is. Okay, so you get one here. Now, by the way, the Symbolab is telling us right here, here's two of them. The minimum is at -1/3 minus 5/27. The relative maximum is at 1/1, but we have to prove it. Okay, so it's not enough to look at the graph. We have to prove it. All right, so let's do that. So here's what we're going to do. The first thing we will do is take the first derivative and set it equal to 0. Okay, so this is very straightforward. We'll use the power rule. 1 plus 2x minus 3x squared. Now, something like this, probably you should rewrite it. I don't know about you, but I think it would be very difficult to factor this. So we may as well use the quadratic formula. It's one of those things where everybody remembers it. You might as well use it. Okay, so what do we have here? Oh, so I forgot to label them. This is A, of course, this is B, this is C. So A is -3, B is 2. So we have -2 plus or minus 2 squared minus 4, -3, 1, all divided by 2 times -3. All right. So then we can simplify it a little. Now, underneath the square root sign, we have 4 plus 12. Okay, 2 squared is 4. But here we're subtracting a negative, so it's 4 plus 12. So therefore, this is 16, which is a sigh of relief for us because you can see that obviously 16 is a perfect square. Okay. So we're going to have minus 2 minus 4 over minus 6, comma, minus 2 plus 4 over minus 6, which is just minus 1. And, oh, sorry, no, the first one is positive 1. This is what I get for skipping steps. Minus 6 over minus 6, comma, 2 over minus 6. And then we can reduce that easily to 1 and negative 1/3 are the so-called critical points. And of course, you can see, if you look at the graph, that looks about right. 1 and negative 3. 1 is here, and it even says so in Symbolab, and negative 1/3 is right here. Okay, so that's where we find relative maximum and minimum. What we're going to do now, though, is we're going to check. So essentially what we're going to do is pretend that we don't know what this graph looks like. Okay. So this one, the minus 1/3 corresponds to negative, let's label this right here. And this one is very easily 1, 1. So what are we trying to do here? We're trying to demonstrate where the function is increasing and decreasing. So how can we do that? Well, what we can do is, looking at the 2 critical points, we evaluate the first derivative at a point before the first point, after, and before the second one. So in other words, I'm going to start with f prime of negative 1. This is going to tell me what the slope is when x is negative 1, which is to the left of this first critical point. And that will give me a clue as to whether or not the function is increasing or decreasing before it reaches negative 1/3, comma, negative 5 over 27. So let's remind ourselves the first derivative. It's way up here somewhere. F prime of x. I'll just sketch it in right here. 1 plus 2x minus 3x squared. So f prime of negative 1 would be 1 plus 2 times negative 1, which is 1 minus 2 minus 3. And that's going to leave us with negative 5, which is negative. Okay. Oh, wait a minute. Sorry. I just realized I goofed right here. No, the 1 is just 1. It's 2 negative 1 minus 3 times negative 1 squared. So it's 1 minus 2. Now, negative 1 squared is obviously positive 1. So this is fine. But that's okay. Well, this is negative 4. Sorry. It is negative, though. So that means the function is decreasing as it approaches this first extremum on the left. So if I then evaluate this function at 0, first derivative rather at 0, I'll have 1 plus 2 times 0 minus 3 times 0 squared. And I'll have 1 plus 0 minus 0, which is positive. So in other words, the slope of this function is decreasing to the left of this first relative extrema, and then it's increasing after that. So what this means then is that it must be true. Just fix this real fast. When the function slope changes like that, what that means is that, hold on. So in other words, what's happening here is that the slope is negative, and then now it's positive. And that indicates that this point must be a relative minimum. Okay, now what about this other one? 1, 1. Well, we already know that f prime of 0 is, from up here, a positive. So why don't we try f prime of 2, let's say. Any point to the right of this 1, 1 is okay. So we're going to have, and again, you can't see it from there. The first derivative is, I'll write it here somewhere, 1 plus 2x minus 3x squared. Okay, so you plug in the 2. You have 1 plus 2 times 2 minus 3 times 2 squared. 1 plus 4 minus 12. Okay, so in other words, the slope went from positive to negative on either side of that point. So that implies that 1, 1 is a relative maximum. Okay. In other words, we don't have, imagine you don't have Symbolab right in front of you. How else would you know if these are maxima or minima? This is not the only way to find out, but this is one way. All right, now, what about the second derivatives? We're interested in knowing where the function is concave up and concave down, as well as where's the inflection point, if there is one. There's not always an inflection point. The inflection point was probably right about here. Because what's happening is that if you look at the behavior of the function just before that point, it seems to be increasing at an increasing rate, and then it's increasing at a decreasing rate. And so when something like that happens, that means the sign, the second derivative is going from positive to negative on either side of this point. That's what it really means to be an inflection point. It's the point where the sign of the second derivative changes. At the inflection point itself, the second derivative is equal to 0. So if we go back to the original function here, let's copy this down here. Let's see. All right, so once again, f x is x plus x squared minus x cubed. F prime of x is therefore 1 plus 2x minus 3x squared. F double prime of x is therefore 2 minus 6x. Now, what we need to know to find the inflection point is set this equal to 0. Okay, 2 minus 6x equals 0. The nice thing about the second derivative is that it's often a very nice, simple function. Okay, 1/3. All right, so if you go back to this graph that I sketched in here, positive 1/3. There it is. Yeah, that looks about right. And in fact, if you do plug this into the original function, you'll see that this is the point 1/3 comma 11/27. So you don't really need that, but you know that at 1/3, when x is 1/3, the sign of the second derivative changes from positive to negative. Now let's prove it. So once again, the second derivative is equal to 2 minus 6x. So let's check out f double prime of 0. Okay, so that means leading up to this inflection point, second derivative is positive. Okay, but after that, let's do f double prime of 1, which is on the right-hand side of this point. It becomes negative. Okay, so that means that the function, well, first the inflection point occurs when x equals a third. The function is concave up before the inflection point, and the function is concave down after the inflection point. So the shape should tell you what you need to know. And if you look at the symbolic graph, of course, it's really pretty and all, but what we're aiming for is to the left of that point. I don't know if they label it here. They label a lot of things, but I'm not seeing the inflection point. We can ask it. Usually, no, here it is. Yes. So in other words, what they're trying to remind you is that at this point, the second derivative is 0. Wherever the second derivative is positive, that indicates concave up, and negative is concave down. Okay. So yes, the function is concave up to that inflection point. Afterwards, it's concave down. Okay, so we're done with this one. Very good. So that was a lot of work, but it was worth it. Okay. Oh, what happened here? I'm using my Rook computer here. It's not nearly as powerful as my home computer. All right, so it looks like we're ready for. Hold on a second. Just want to make sure I didn't lose one. Oh yeah, let's go back to the document. There it is, 437, number 268 and 270. So what are those all about? So I'm going to guess 445. It's kind of a guessing game. Oh, boy, I was lucky that time. Oh my God. So this is number 268. And what we're trying to do is solve for the limit. Okay. Now, we've encountered different kinds of limits. So let's see what this is all about. So we have number 268. The limit as x goes to infinity of 4x over radical x squared minus 1. Now, if you notice, this one, you can't really directly substitute infinity in here. It's not going to work. So when you have a case like this, where there's x's in both the numerator and the denominator, usually your best strategy is to divide the numerator and the denominator by the highest power of x that you see. Even if that doesn't work, you can try different powers, but often you're aiming for the highest power. Now here, because the x squared is under the square root sign, why don't we do this? The reason for that is because the limit, what you're really aiming for is this. You can help yourself a lot. If you end up with something like this, that reduces nicely to 0. And this is really what you're trying to accomplish. You're trying to sort of simplify, and so that the terms may look something like this. Now, first things first, we can factor out the 4. That's not such a big deal, but it sometimes can help you avoid mistakes if you move out all those pesky constants. So what we're going to do now is something a little strange. We're going to divide And of course, we're allowed to do this without changing anything. Divide by x in the numerator. Now, the numerator is pretty straightforward, but what's happening here? What you can do is this. Rewrite x as square root of x squared. And then what you've actually got here is this. And then, okay. Okay, so in other words, what we're going to do is rewrite this as one over this. And you might say, well, what in the world did we just accomplish? Well, remember, if you plug in the infinity for that x, 1 over infinity is the limit of that is 0. So in other words, all of a sudden, we're all set because you've got 4 times 1 over radical 1 minus 0. And you're done. You've got 4. So the trick was this, by the way, this was not meant to be a L'Hopital's rule because it wouldn't make things any simpler to use L'Hopital's rule. Instead, you're using the technique where you divide the numerator and the denominator by what, usually the highest power of x. And the whole idea is to reduce all these terms so that they go to 0. Okay, if you are successful, you'll end up with a good answer. All right. Now 270, I think, is very similar. Man, look at all those questions. Yeah, but we covered a lot of material here. So anyway, 270, let's go back to the book. Same idea, it's limit x goes to infinity. Lim x goes to infinity of 2 radical x over x. Now this one, well, all right. Well, it's going to be very similar. It's just a little bit messier. So, all right, let's do this. Let's move this 2 outside. So let's just divide everything by x, okay? And also keep in mind, little side note here, radical x over x is the same thing as x to the 1/2 over x to the 1. Okay, very good. So now you can see we may end up in pretty good shape because the numerator will be 1 over radical x. The denominator will be 1 plus, minus, again, 1 over radical x plus 1 over radical x, just plain x, sorry. And so then we're going to have, and now we just substitute. This will be 0 in the numerator, 1 minus 0 plus 0. All right, so we just end up at 0. So again, the whole point of it was that we have to use our cleverness to do this. Now, these next two, I don't remember what happened, but let's just say that There's such a catastrophe that I've decided that we don't want, we'll just toss these out. Okay, they won't be on the tester because I just realized that there's such a mess and that we really didn't do any like this. So we're just going to skip over those two. They looked on paper very harmless, but I just realized after the fact that no. They're a bit much. Okay, now 564. So let's go for 572 and see what happens. Oh my God, I'm getting pretty good at this. So number 184 is right there. And you can see you need to take a definite integral of secant squared theta d theta. Now, here's where you get a break. If you're intimately familiar with the slides, you'll discover, and you should have them right in front of you when you're working on this test. Where are we? Slide 4D, chapter 4D, I called it, although this one is the corrected version. There's one trivial typo in there somewhere. But slide 23 has a chart of the trig integrals. Okay, so that's what we need here, trig integrals. Now, the one we need is secant squared. And guess what? This one is already here. The integral of secant squared x is simply tangent x. So guess what? We're all set. Of course, we still have to evaluate it, but we're going to have tan theta. Now, this notation means that we're going to take the tangent of pi over 4 and subtract the tangent of 0. That's what we're actually doing here. We're evaluating it at the limits of an integration, as they're called. Now, if you look these up in, if you go to your calculator, or if you go to the book or Symbolab, this is equal to 1 minus 0, or just 1. Okay, and that's that. So don't forget. Okay, so yes, there's a lot of important formulas in those slides. I've summarized them for you so they're easy to find, but you know, what you might want to do, like I said, is if you're starting to forget where everything is, flip through the slides before you sit down and work on this thing. Now, there's no time limit, of course, but it'll go easier if you already can remember where to find what you're looking for. All right, well, that was nice and easy. Now, in 575, these are also very straightforward too. We have formulas that we can lean on if you don't remember them. Also, just don't forget too, the odd number answers are in the back of this book. So you can double check this with the book too. So 575, let's go back to the book. Oh my God, I did it again. Okay, 209, you can see there's an integral of dx over 2x. And again, you know, because sometimes the constants are distracting, they might prevent you from noticing that, hey, wait a minute, this is one we saw all the time. This is the exception to the power rule. Remember the power rule for integrals. The integral of x to the n is x to the n plus 1 over n plus 1, as long as n is not -1. In this case, it is. Okay, the exponent, x 1 over x is the same as x to the -1 power. In that case, we have log absolute value of x plus c. And so here, because of that 1/2 on the outside, this one is simply 1/2 log absolute x plus c. And that's it, you're done. Wow. Some of these are really straightforward, but you have to remember, that this is the natural log case. Okay. What about 211? Oh, trig functions. All right, so if you look at the book, it's right here, it's the same list. It's 0 to pi sine x minus cosine x dx. Now, you might recall that algebraically, this is equivalent to sine x dx minus cosine x dx. And furthermore, if you were to take a peek at slide 22 on chapter 4D, you'll remember that we have our trig integrals, which we were just looking at a minute ago, but we have these two. Just a quick reminder. The integral of sine x is cosine x. So we're going to evaluate that from 0 to pi. Now the integral of cosine x is negative sine x. Let's go prove that. Negative, oh wait, oh sorry, I missed it. I got the wrong one. Sine x is negative. All right, my fault. This should have been negative. That's right. I got them backwards, sorry. The integral of sine x is negative cosine x. And the integral of cosine is positive sine x. Yes, now we're all set. All right, now we're good. So we'll have cosine pi minus cosine 0. And remember, this negative is out here. And then we'll subtract sine pi minus sine 0. All right, so if you look these up, unless you have them memorized, cosine pi is -1, cosine 0 is 1, sine pi is 0, as is sine 0. So the bottom line is that it's 2. Okay, well, that wasn't so bad. All right, what's going on page 592? By the way, of course, I'm going to post a copy of these notes on Moodle, so you can go through them and read them. I mean, you should watch the video, of course, but you can go through these and double check and see how you did. All right, so 592. Let's see, I'm going to go for page 600. Oh my God, I'm getting so good at this. All right, so the one we want is number 268. Now here they're being helpful with us for some reason. This is meant to be done with, not only is it U substitution, but they're even telling you which one to use as U, which is a little unusual, I think. I don't remember seeing that before. But you know what? You take all the help you can get. All right, so you've got x squared minus 2x times x cubed minus 3x squared, all squared dx. Now, normally when you choose a u in a case like this, you see how you have two different polynomials. You normally choose the one with the highest degree anyway. But this is what they're telling us to do. They're giving us a hint. So this implies that du dx, based on the power rule, is 3x squared minus 6x, which means that du is all of this dx. Now, we don't quite have that, do we? We need this to take this form. But the only thing that's missing is a 3. Okay, now we can supply the 3 ourselves. So here's what we're going to do. We'll rewrite this as 1/3 times 3 and then we can rearrange it just a little bit. And the nice thing about that is that you can see that this is du, this is u squared. So look how easy this is. 1/3 u squared du So we'll have u cubed over 9 plus c. And of course, remember, we defined u to be x cubed minus 3x squared all over 9 plus c. Okay, so remember, u itself is just the x cubed minus 3x squared. It doesn't have an exponent. So that's our final result. Now, 276 is very, very similar to this. It's u substitution. And again, for some reason, they felt the need to help us out by telling us what to do. Okay. People help you, do not ask questions. Oh, actually, I think this is the case. They don't help us. We have to figure it ourselves, but they do tell us, I believe. It says a suitable change of variables. That usually means u substitution. So here's all we have to do. We've got sine 7. That means sine theta to the 7th power, cosine theta, d theta. So here's what we're going to do. Based on the charts, from way back, I don't remember exactly which slides they were on, but we saw that this derivative of sine theta is cosine theta. So let's do this. Remember, we usually try to let u be the, whatever has the highest exponent. So let's try u equals sine theta, then du dx. Actually, it's du to theta. Oh, I just realized I did the same thing here. It's so easy because you're so used to x's. But with trigonometry, we often end up with thetas. And so that implies that du is cosine theta d theta. So the original problem now, oh, sorry, hold on, I missed the cosine. Can be thought of as u to the 7th. We just neaten that up a little bit. Du. And so we have and of course we defined u to simply be sine theta. And that's it. Oh, that was nice. Nice and easy. Okay. Yeah, we got off to a rough start here with these questions, but we're starting to see that a lot of them are not too bad. I picked a few that I shouldn't have, but sometimes, it's not always that obvious. You look at it later on and say, wow, that's a mess. Okay. Now, here's what I'm going to do. I can tell I'm running out of space by how long it's taking to save this document. So what I'm going to do is I'm going to actually save this and close it up. The one thing we have to watch out for when writing with a tablet like this is that it really takes up a lot of space. And this computer that I'm using right now is quite small. It's a little tight with the memory. So what I'm going to do is rename this part 1. Because I've run into this problem before, and believe me, it can be a nightmare. If you run out of space, you could actually lose all of your work. So what I'm going to do, first of all, I remind myself where we left off. All right, so we were just getting ready to do 605. Okay. So what I'm going to do is put the rest of it on the second document. I'm going to open this up and resave it. Okay. All right. No, we don't have to worry about anything anymore. Okay, we have plenty of room. So 605, number 322. Yeah, we could have been here all night trying to pick apart all the information we had. Oh wait, what did I do? 605. Let's try 612. No, not quite. Here we go. Here we go. So all we're doing is calculating indefinite intervals. So number 322 is 2 to the x dx. Now, this involves a special set of rules. Now, here we're dealing with the end of chapter 5. So let me just remind you, if you look in 5, specifically 5D, this one. Yeah, this is the last part of 5. This is where we started talking about integration for functions of this form, either e to the x or a to the x. So the one we need is this one. I'll just copy this. You can see it's the same thing. Okay, we'll give it a minute to catch up. Sometimes those equations can also take up a lot of space. This, like I said, this computer, it's the kind of thing you bring with you when you're traveling, because if let's just say it disappears, you're not that worried about it. All right, so that means that you can see that in this case, a is 2. So we end up with 2 to the x over log 2 plus c. And that's it. That's all you had to do. All right, now, 326 is next. All right, oh, look at this one. This one couldn't be any easier. I can't believe it. Okay, so just remember that this is the power rule, because this is the same thing as x to the minus 2 dx, okay? So don't forget our old friend, the power rule. Because n is not equal to 1, a negative 1, that means we can use it here. Okay, and this is the same thing as writing. If you'd prefer, you could write it as this. And you're done. Beautiful. Now, the next one is, what was it? 338. All right, what is that all about? Ooh. Now, this one's a little, at first it appears scary. Now, this one, you may remember we had, well, actually, let's see, maybe we had this in our slides. I don't remember the exact location. We have e to the x dx here, but we need e to the g of x. I'm not sure if we have a specific example of this. So let me just show you what this is all about. Whenever you have something like this, you're going to wind up with e to the g of x plus c. Now here, as you can see, if you let sine of x be g of x, then cosine is g prime of x. You have exactly what you're looking for. So that means that the final answer here is just e to the sine x plus c. Again, if you're not sure, when you do something like this, whenever you integrate, you can always double check You say, well, wait a minute, I'm not so sure about this. Remember, the way this works is that the derivative of e to the g of x is e to the g of x, g prime of x. So in that case, the derivative of e to the sine x, we don't have to worry about the constant. Obviously, that goes to 0. And that's exactly what we started out with. So that proves that we must have done this correctly. Okay, good. Now, oh, the 730s. As those page numbers get large, it stands to reason that these questions are going to get a little more challenging, but not necessarily. All right, so 732, 296. Oh, I missed it by 1. Okay, my streak is over. Oh no, you know what it is? I didn't, that's not what happened. I made a typo. There we go. 732, number 296. So they want us to just simply take the derivative. Okay. So what do we have here? So basically, whenever you have something like this, somewhere along the way, and again, I don't remember exactly which section this was in. This implies whenever you have log of some function of x, the derivative is 1 over g of x, g prime of x, or you can just write it as g prime of x over g of x. It's very straightforward. So in this case, since g of x is 2x plus 1, that implies that g prime of x is 2. And so our final result, if f of x is log 2x plus 1, then f prime of x is very simply 2 over 2x plus 1. G prime of x over g of x. All right. Now, the next one is number 298. All right, what are they asking us for? It's the same type of problem, except that it's dt over 3t. So let's write it like this. And oh, wait a minute, guess what we have right here? That's that special case. It's the exception to the power rule. Yeah, it's just the 1/3, we bring it outside, and then we have the natural log of the absolute of t, absolute value of t, and we're done. And then number 310 is oh, same thing. All right, this is a definite interval though, from 0 to 1. Dx over 3 plus x. So you know what? It looks kind of strange, but not necessarily, because what you've got is a natural log case, because you can think of g of x Yeah, so in other words, because it's in that form. Now, how do you know that? Because we have just plain dx up here. So in other words, if you let g of x be 3 plus x, g prime of x is just 1. And so therefore, you do have g prime of x dx is just dx. Okay, so you're good. All right, so you end up with and that's it. Oh, I almost forgot. What am I saying? This one is a definite integral. It has to be evaluated. So we can drop the c. Okay, this was meant to be an aside. So we don't need, sorry, we don't need the c. All right. From 0 to 1. Now, because these are positive numbers, we can drop the absolute value signs. And that's it. We're done. We can't really do anything. I mean, you can rewrite this if you want. Using the properties of logarithms. But that's as simple as you're going to get it. Okay. Okay. Was there one more? Yes, 322. So these are derivatives, okay. Y equals e to the sine x. So what are we supposed to do with that one? Well, now remember, so if g of x is sine x, so the final result, if y equals e to the sine x, dy dx, dy dx, e to the sine x cosine x. All right. Now, we got a few more. Now, these next two are applications from chapter 6. Okay, chapter 6 has several applications in it. So for 352, ooh, some nice graphs here. This is, by the way, we're looking at this exponential growth and decay model here. So, all right, I need page 743. Should be right down here. Number 352, there it is. I wonder if it'll let me copy. That would be nice. Oh my God, it did. Okay, now what's going on here? So they're telling us, now, first of all, the function, this is exponential growth. So remember, this is the initial value of whatever it is that we're looking at. This is the growth rate, or growth constant, they call it. And this is time. You can think of this y as the final value. And we can rearrange this thing and solve it for whatever we need. So what they're doing is, first they're telling us that the doubling time is 3 hours. So in other words, if we could think of this as y0 is 1 and y is 2. and t is 3. Okay, in other words, to go from 1 to 2 in 3 hours. What we do here is solve for k. Okay, now, and that shouldn't be too hard. But we will need logarithms, of course. Remember, so we divide both sides by 3. And so the growth rate is log 2 over 3. Now we're not done because they want to know how long would have to elapse before the bacteria colony has multiplied its original value by 10. Okay, so now we know that k is log 2 over 3. Y0, we can think of it as 1 and y could be 10. Okay, so we have, and by the way, this is growth, so we have a positive exponent. Decay is the one that's negative. 10 equals 1e to the log 2 over 3 t. And remember, now we're solving for t. So this means that log 10 and so when you're done, this is the actual answer. That's how long it takes for the colony to have multiplied by 10. Now, if you were to plug that into a calculator, this is approximately equal to 9.97 hours. Okay. Now we have next, let's see, what's next? 354. Now this one is a little bit trickier. We have to be very careful with it. Here's the whole point of it. Somewhere in the slides, in 6, they mention this, 6A or B, that with these types of problems, the concept of the half-life is very important. You heard that in high school physics. How long does it take for the radioactive content of an element to reduce to half its original level? The half-life is log 2 over the growth rate. Okay, so that's an important detail. So again, log 2 over k. They're telling us that that's equal to 5730. So every 5,730 years, the amount of radioactivity is reduced by a half. So that implies that the growth rate in this case and it's a tiny, tiny number, 0.00002 or something like that. Now, here's what they want to know. How old is the skull, which contains a fifth as much radiocarbon as a modern skull? Okay, so again, remember, this is the exponential decay problem. So therefore, we have this negative. And so we had whatever we are now is 1/5 at the starting point. The growth rate is log 2 over 5730. And t is, of course, what we're aiming for. And so you just solve for it. Now you might say, wait a minute, can time be negative? No, but the thing is, the log of a fraction is always negative. So you'll actually end up with a positive number. And this one is approximately equal to 13,304 years. Okay, now there's one more listed here. The only unfortunate thing is, and it's kind of a fun problem, but Unfortunately, we didn't really get to this one because what they're actually asking for is not the future value of a sum of money. They're asking about what's called an annuity, which means that you're withdrawing money every year for so many years. And we didn't actually get to that. So we're going to leave that one out too. Okay. So that one's done. So anyway, that means we've covered all of the ones that will count. Okay. There's about 3 that I had to drop. So anyway, what I'm going to do is, of course, post the recording. Oh, I just realized this one also needs page numbers. Jeez, like I said, it doesn't assume you want page numbers. Let me take care of that right now before I forget. Yeah, we're good. Okay, so there's 2 parts to it. I'll post these in the video, and then you'll be ready to roll. I'll post the actual final in a day or so, I guess. So we have to be careful. I'm going to post an announcement, but the class is actually ending sooner than I realized. We don't have that much more time left, so we're not going to do anything new. Everything through chapter, if you look at the slides, chapters 6A and B are the final slides that we'll be doing. And I have to have everything in by, let's see, Monday. I think it's Monday. Hold on. Let me just double check the calendar. Okay. I don't know what's going on here. Oh, wait, we almost had it. Like I said, oh, what are they doing here? That's 21. Here we go. All right, I'm not even going to click it on. You can see. So it looks like Monday the 1st. All right, so here's what we're going to do. Everything that isn't done yet will need to be done by Monday the 1st. Okay, because the school is very rigid about the cutoff point for the grades. So the last assignment, which is chapter 5, I believe, and the final must be handed in no later than midnight, August 1st. Okay, only to make sure that you get your grades on time. Okay, so I'll make announcements and I'll make sure that the final is ready very soon. It won't be as long as this, that's for sure. Just to make sure you understand what we did. And then we'll be done. Yes, we will. Okay, so, all right. So I will go ahead and post this now. And then within a day or so, you have the final exam ready. And then when that's done, we're completely finished. All right, so, well, I hope you had a good experience here because we covered a lot of good material. And you have all the slides and you can go through them as much as you want. And once you get into Calc 2, you'll certainly need to remember everything we did here. So you might want to flip through them and review on a regular basis before Calc 2 starts, because they will dive right back into where we left off. They'll probably start with some much more complicated integration problems before they go on after that. So, all right, well, good luck, everyone. Good night.